There she is. Okay. All right, let's get rolling. So where's my marker? There she is. So let's start with the opener. So just a little review from last week. This would also be a good time to tell you that this coming Thursday, you will be taking an assessment. I guess technically you can call it a test, but really it's just like an assessment. It is the thing that's worth a bigger chunk of your grade, but all that's going to be on it are problems like this. So just like literally what we've been covering these last few days, and we'll cover Monday, Tuesday. Wednesday will be a review day. Recall Wednesday is like a non-Zoom day. We just have office hours. You're going to have like a review that will be released that day. I'm going to try to put it on there actually today, so you guys have early access to it. And then we'll have some stuff to help you out on that day as well, right? So that being said, let's attack this. So first of all, what is the actual geometric idea that applies to question 1? I can't see the chat from here, so you're going to have to call it out. Oh man, we're going to have an awkward silence. So what I'm looking for is like when I say the geometric idea, what I'm looking for is like a rule, a definition, a postulate, something that applies to this picture. You can certainly have your notes out. That would help. I'm looking for an answer.
Are we like looking to solve for like the segment addition postulate?
We absolutely are. So we're looking to use SAP or segment addition postulate. Like even if it seems obvious, like what's the thing that you're seeing in this picture that says, yes, absolutely, that's what I'm using?
Line segment with A, B, and C, and it says solve for X, and you have the values of A, B, BC, and AC.
Yeah, no, I'll totally take that. I mean, so like the thing in geometry that you really have to pick up on really quick is that the structure or the picture is going to inform like what to look for, and then what to look for is going to inform how to solve it. It's very much like a 3-part thing. And so like the thing that you should attach yourself to is that you have a segment, AC, that's divided into 2 subparts, AB and BC. More so, you don't know that B is precisely in the middle, so segment addition postulate will be the relationship that applies here. SAP, which of course stands for segment addition postulate. Okay, now the segment addition postulate, and recall that postulate just means rule. It just says if I have a whole segment, I can add up the parts and it's equal to the entire segment. And so hopefully we've been given like enough stuff to do that. Let's double check it. So we have AB is equal to 4x plus 9. When AB is written in this way, to what does it refer?
Segment AB.
It actually doesn't refer to the segment AB. It actually refers to something about the segment AB. If it were the segment AB, it'd be written with that symbol, but it does not have that symbol, so it has to be something else. What is it?
The length of segment AB?
Yeah, absolutely. Whoever said that, very good job. In fact, that's one of the most mistaken things in geometry is that like when you see this notation at the symbol, it's just referring to a length. And so when you see this 4x minus 9, that refers to the length of AB. It's variably defined because we don't know it yet, but certainly through the course of problem, we can totally find it. Do we know the length of BC, the red segment? Yay or nay?
Yay.
Okay, so what is it?
5x plus 2.
Yeah, that's given to us in the problem as well. So the length here would be defined to be 5x plus 2. And then to complete the segment addition postulate, we're going to need something to compare it to, and hopefully that's going to be the whole length. But we're afforded that. That's going to be 56. Okay, so the rhythm is that we see the structure. We see segments cut into parts. We know the relationship, segment addition postulate. And now that should inform an equation. Now, sometimes I like to think in terms of equation frames. And so I know that the segment addition postulate says if I take the parts, I can add it up to make the whole. And so I know I'm going to basically be filling in this equation or this equation frame where this is going to be part of the segment, this is going to be part of the segment, and then this should be the whole segment. So having said that, and hopefully you're catching on to my color coordination, what should probably go in the first blank?
4x plus 9.
Yeah, it should. 4x plus 9, because that represents the partial length AB. In the second blank,
5x plus 2.
that represents a partial length BC. And then 56 should, of course, go in the whole, because that's the entire length AC, which is when you get like this variably defined equation, AB plus BC equals AC, which is just part plus part equals whole. Give me a thumbs up either virtually or like on your camera if you get what I'm saying. Sweet. Okay. So now it's just an issue of solving it, but this is just now algebra, so we can go quick. So we have these two x values. That'll make a 9x. We have 9 plus 2 more. That'll make 11 equals 56. Okay. So if we subtract off the 11, well, we'll have 9x is equal to 45. Divide out the 9. We have x is equal to 5. Okay. Now, pay really close attention because you'll have problems of all different varieties. Sometimes we'll just say, hey, find the x and that'll be done with it. But ultimately, we're finding the x for a purpose, and that purpose was to know these lengths. And so, like, how do I take this x equals 5 and determine the lengths of my original diagram? What shall I do?
You plug them into the x spot.
Yeah, no, absolutely. So just plug them in. And so this becomes a 5, and that becomes a 5. Okay. So 4 times 5 plus 9 should be, what, 29 for this segment. We have 2 different ways we can figure out the last segment. Give me one of the 2 ways we can figure out the last segment. The red segment. I would say there's one brute force way that we can find out the length of the red segment. There's also one finesse way. What's like the most straightforward algebraic approach way to find the red segment?
5 and 5.
Yeah, just do the same thing we just did, right? 5 times 5 is 25, plus 2 makes 27. What's the sneakier, more elegant way to find the value of the red segment?
Subtract AB from AC.
Yeah, so just go right back to the segment addition postulate, right? And so if it's the 2 parts added together, certainly 56 minus 29 should also give us BC. Which is also a way to confirm your answer. And so I can tell you, like when I'm personally working these problems, like for you guys for a key or something, I do it both ways. I substitute and then I double check with subtraction. Okay? But either way, we have AB is equal to 29. We have BC is equal to 27. And that makes AC equal to 56. Okay? So really small hitch in the problem number 2. It's just like problem number 1, except, well, I forgot to give you the diagram. So like, what's the obvious first step here if we don't have a diagram? Oh, you guys doing the awkward silence thing. What should I put on the problem first, since it's not already provided?
Diagram.
Yeah. And so you have to do some intuitive thinking. This doesn't actually say that they're all lined up or in order, but I think that's probably a safe assumption for most of these problems. So here I have A, here I'm probably gonna have C. Now a student asked last week, excuse me, where should I put B then? Because it doesn't really say where B should be. And it's certainly not as safe to assume it's in the middle, like smack dab perfectly in the middle. So where should I put B?
Closer
Or
to
tell
C.
me, I'm sorry, what was that? Brett?
I would say either slightly to the left or slightly to the right.
Okay, which one? Or accuse me of asking you a trick question. Do one of the 2 things.
Slightly to the left because it's got
Okay.
a 4 to be, which mean it would be bigger.
Okay, and so like you're kind of using the numbers to intuitively decide where to go. Why is what I'm asking you guys really a trick question?
It's just
Because
the
we
same
don't
problem
know.
from up above.
Yeah, and so think about what the problem's asking you to do. It's asking you to figure out some values. It's not asking you to make a perfect picture. And so what we actually just need is a representation of where B could be. And so Brett's asked me to put B here. I think that's totally fine. We could put B here. I think that's also totally fine. We could put it way the heck over here. That's also totally fine. Because we don't really know where B goes. We're just trying to represent the situation. And remember, the situation segment addition postulate, part plus part equals whole. And so where the placement of B is doesn't necessarily matter. It could be wrong, and we could still actually get the right answer for X, A, B, B, C, and AC. Okay, and so I'm gonna. That's where it landed last. That's where I'm gonna put it. So the next thing we should probably do is label our diagram. And so we have AB is 2x minus 1, or 2x plus 1, excuse me, in quantity. We have BC to be 3x plus 1. Okay, and then we have 4x plus 2 to be the entire segment. All right. But as far as like how this is set, how the setup goes, it's going to be the same. So we have a part AB plus a part BC is equal to a whole AC. Okay, so now comes as far as the substitution. AB should be the same as 2 times a quantity x plus 1. BC should be the same as a quantity 3x plus 1, and that's positive, so I'll keep it as a plus sign. And then AC is defined to be 4 times a quantity x plus 2. All right, so they try to throw a little wrench in here to get you guys to mess up with the parentheses. But you guys know how to handle that. What's the term, starts with letter D, that helps us handle these parentheses?
Distribute.
Yeah, so let's do that. So 2x plus 2, the same as 3x plus 1, the same as what, 4x plus 8. And now we just continue as we've always continued algebraically speaking. We should probably simplify the left-hand side. Let's get all our x's to one side. Okay, so looks like we have another x equals 5 situation. Okay, before we finish this last part, same thing. Can you guys just give me like a thumbs up? I'm totally with you, Collins. If you have a question, now would also be the time to ask it. So like if you have a ponderance, throw it out in the chat, or well, like, don't throw it out in the chat. I can't actually see that. But like just unmute your mic and ask it. Cool. Can everyone then take 30 seconds and find the 3 length values? So in 30 seconds, can you please produce for me AB, BC, and AC? Okay, someone please call out what the value of AB is.
12.
Well, BC is,
16.
which makes AC
28.
28. Very good. I'll confirm all 3 answers.
Something.
Sweet. All right, Zoom, entire page. Okay, so just a little review. Notation is always going to be in play, so we have to be careful with notation if we're talking about a segment versus a length versus whatever. Make sure we're noting that properly. We know this is segment addition postulate because we have a segment cut up into multiple parts, and those parts are not necessarily equally divided. Therefore, the structure tells us we're using segment addition postulate. Segment addition postulate tells us that our end equation should basically be, that didn't work, should be something plus something equals something. There could be some algebra variations where we have like distribution that we have to handle, but in the end, you're still really just setting up an equation where two things add together to make a whole and solving for it. Okay. So this one, since now with my computer, can either in the chat or just visually, can you give me a rating 1 out of 4? Like 1, I'm feeling, or 4, I'm feeling really great about this, Mr. Collins, Ms. Jaco. 1, I'm still super lost to segment addition postulate. Sweet. Okay, I'm seeing mostly 3s. I appreciate the 3.5 and 4s visually too. Okay, I think we're ready to move on. All right. So today what we want to do is install some more relationships. We kind of said this whole beginning part was about like, oops, there we go. This whole beginning part of geometry was really about understanding the language of geometry. And big piece of language of geometry is understanding how parts interact with one another. So moving forward, that forms the basis of our whole study. Okay. So this is the part where I need you to prepare some notes. Yeah, because we're going to take notes. I wish that you guys were in classless so we could do this kind of a different way, but that's just the way it is right now, guys. So we're going to have to give you some information. So let's take, let's say 3 minutes, maybe 4, and just get set up in your notes. If you're prepared to answer the first question because you know the difference between acute, obtuse, right, and straight angles, don't wait for me. Just go ahead and jot those things in, and then you can add what I'm going to add to. Okay. So let's begin at like 9:20 until I give you guys a chance to kind of set your notes and get ready. Hey, everybody. Let's talk about angle relationships. So in geometry, there's really two big subcategories of things we study. Angle relationships and side relationships. When we get deeper in the semester, we start studying something called trigonometry. Those two things are going to start to mix together. But for now, we're going to keep them fairly separate. And so the big question that you need to answer before the end of today, and this has been amended. There are actually 4 major relationships between angles and geometry. And of course, we're going to talk about how to use them. I do appreciate some of this is going to be review from stuff you've seen before, but this is really an effort to formalize stuff. So just as a point of order, an information starting point, so to speak, when we talk about acute angles, how do I differentiate those between the rest of the angles?
Acute angles are less than 90 degrees.
Yeah, so we're going to use some math symbols here, and so that's less than 90 degrees. Okay, so that's less than the way I'm using it. Okay, and so like for an example, something like this. Okay, like that would be an acute angle. What is an obtuse angle?
Larger than 90 degrees.
So it's got to be greater than 90 degrees. Okay, so this is greater than. Okay, and so a nice example would be something like this. So a wide open angle, boom. A right angle?
90 degrees.
So it's equal to 90 degrees. And so it would look like this. We're familiar with that when we talk about perpendicularity. And then a straight angle. Maybe less familiar, but certainly one you can intuit, maybe.
180 degrees.
It sure is. So it's equal to 180 degrees. In other words, it's a straight line. And so this is kind of in that same category as like opposite rays, excuse me. It's just you're just talking about a line. But what's important to note is even on the straight angle, we are talking about the angle itself, not the lines that form it. And that's going to be a switch from what we talked about before in terms of focus. We're definitely focusing on the angles. So just as a point of vocabulary, when we talk about those terms, that's to which we're referring. All right, so what's the big idea? Like the thing that you're about to see in your notes, what's the thing that guides it, that structures it, that helps to understand it? It's going to be a 3-part relationship that we kind of actually talked about in the opener. And so the thing that you look for first by far is structure. Okay, so geometry is a visual study, and part of you getting good at it is looking at a diagram, looking at a situation and saying, this is what I see with the constructors. Okay, the reason it's important to find the structure is that structure is going to tell you the relationship itself. Okay, so you see something, then you hook a word onto it, like segment, addition, postulate, for example, or one of the words you're going to learn today. And as soon as you know the relationship, it's going to tell you the equation. Now, the end goal isn't always an equation, but guys, this is mathematics. We're going to be doing quite a bit of solving. And so this 3-part relationship is going to be something that's going to become very important to us in terms of how we kind of think about and structure our thinking. Now, the good news is that this is not a new idea for any of us. This is something as human beings we do all the time and very quite naturally. So a non-math example, let me just kind of help you visualize something. So like you're walking downtown Columbia, maybe when you're back in the halls of like Battle, and you see 2 people walking next to each other. Okay, that's like noticing the structure, like you're seeing something. Now, just because you see something doesn't mean you've actually defined it. And then attaching a relationship to what you're seeing is the next step. And so if you see 2 people walking downtown or 2 people walking down the hall, and you say, oh, that's a relationship of being a couple, okay, being romantically involved, as soon as you identify that as being the relationship, all of a sudden you know a bunch of rules that go along with that relationship. You have a lot of behavior that you expect with that relationship. Okay, so you see 2 people, you identify them as being a romantic couple, and then you can predict how they're going to act. Well, that's what's going on right here. And so we look for structure. That structure is defined in a kind of relationship, and the equation tells us how we expect it to act. Okay. And so how can we quickly now apply that into our study? Okay. Also, side note, if I'm going too fast, you're going to have to slow me down because I'm just going to keep on going because it's like I can't read your faces like I could in class. And so if I am going too fast, slow me down. It's not going to offend me at all. And so thinking about the structure relationship equation kind of synergy, The first relationship I want to study or have you guys understand is something called vertical angles. So I'm going to give you the definition of vertical angles, and then we can like discuss it. Okay, so take a few seconds and write that down. Okay. So I'm going to stop sharing for a second so I can take up your whole screen for this demonstration. But vertical angles are angles that occur across from each other at an intersection. Like there's no mystery about intersection. So intersection is literal. So let's say I have like a line or a line structure, right? I'm going to use a ruler for these demonstrations. And then I just simply cross it with another one. Of course, where they touch, where they cross, where they overlap, that's the point of intersection. That's just a general idea what the term intersection even means. So when we talk about vertical angles, notice please at this intersection that there are actually 4 angles. This one here at top, this one here at bottom, this one here on the right, and this one here on the left. And then that might be mirrored, so my left and right might be opposite of yours, but you get the idea. There's 2 here, and there's 2 here. Okay. Now, when we talk about vertical angles, why I call them scissor angles, is you have to understand the relationship of scissors to understand the relationship of verticality. Okay, let's not worry about the terms too much. And so let's say these were a big pair of scissors. Okay, and these 2 pieces were the handles, and these 2 pieces are the blades. If I want to close the blades, what do I do?
Move them closer.
I'm sorry?
Move them closer together, the 2 sides.
Yeah, no, but how do you close the blades of the scissor?
Open the handles.
Yeah, like hopefully you're not over here handling the sharp parts. Like that's something I hope like your parents would have warned you against at some point as your kid. But like, yeah, you totally take these handles and then you do this. How do I know that doing this is gonna close the blades?
The force of the action.
Yeah, but how do I know that like moving the handles this way are gonna close the blades on the other side? Like if these are the handles, right here, and I want the blades to open, what do I do with the handles? I know it seems obvious. Just tell me
Push
the
them
answer.
apart.
Okay, but how do you know that? Like, how do you know that if I take the handles and I spread them apart, the blades won't actually close instead?
Because they're
straight lines.
Continue.
Yeah, okay. So the straight lines connect in the middle. In science, you might call these levers, right? Like that's actually the term for it. And so what you're admitting is that there's a relationship between like the opening and closing of the handles and the opening and the closing of the blades. And more so, if I close the handles, the blades close. If I open the handles, the blades open. You guys with me on that? Okay, so having said that, so what's got to be true about this angle right here, formed at the handle, and this angle here, formed with the blades?
They're the same.
They've got to be, right? In the same way that the angle at the top, how does it relate to the angle at the bottom?
They're the same.
Yeah. And here I have like a real pair of scissors. I guess I could use these too. But like if it doesn't function in the exact way as you predicted, then you don't actually have functioning scissors. Capiche? Yeah, Mr. Collins. Good. All right. So let's talk about vertical angles then. So the first thing that we need is going to be an intersection. And so there's nothing special about a vertical intersection. It could be simply something like that. Like that is a typical picture for vertical angles.
Mr. Collins, can you share your screen?
Oh, yeah, totally can. Sorry about that. Womp. And we're back. Okay, so let me just back up though. So this is going to be like the typical picture for vertical. There's nothing special about it. The thing to note is, again, we kind of form 4 angles. We have this angle at the top, which I'm going to call 1. That can be angle 2. That can be angle 3. And that could be angle 4. Okay. Just so we understand what you just saw, can you please notice that I have different number of arcings on each one? If the arcings match, what does that tell you about the angles?
They're congruent.
So we know that angle 1 must be congruent to angle 3. And likewise, angle 4 has to be congruent to angle 2. Okay, and that's the basic relationship of vertical angles. It has to be. Okay. And in terms of like why call them scissor angles, well, certainly you can kind of look at these to be like the blades, the handle of the scissors. These are like the blades of the scissors, and it behaves the same exact way. Okay. All right, so if we see this kind of in a live example, we see certainly we have an intersection, and then we have two angles in vertical. They're sometimes called opposite angles for what it's worth. I honestly think vertical is the weirdest thing to call these angles, but I don't make the rules in geometry. I just have to live with them. But these are definitely going to be vertical angles. Okay, so that structure implies a relationship. Now, I heard the word same said a couple times, but what's the actual term for structurally identical?
Congruent.
So vertical angles are absolutely congruent, which informs an equation. If we have something that's congruent, we know that they're equal in measure, and so I'd expect something equal to something. That would be my sentence frame or my equation frame. In this particular case, what two things are equal? So for this example, what two things are equal?
The
The
line.
opposite.
Yeah, so please name them. Like, so what values should be equal?
Three x should be equal to 2x plus 16.
Absolutely. So we have this angle, and that little. So when you see this, it's a degree mark. So we know it's something in degrees, but that's totally normal for four angles anyway. Okay, and then we have this other vertical piece defined to be 2x plus 16. Okay, so structure tells us a relationship. Relationship tells us the equation. The equation explains the diagram. So in terms of what we do now, we're just going to solve. So we take away 2x from both sides. We have an x equal to 16. Okay, now of course, x is not the angle value. X defines the x value only, the unknown. How do we find the angle values?
It's like an X.
Sure, we sure would, yeah. And so we have 3 times x. So 16 times 3, this would be 48 degrees. So what must the other angle be automatically?
48 degrees.
Yeah, and if we type that in, we can confirm that's also 48 degrees. Okay, so that's vertical angle. So you have an intersection, you have 4 angles. They are congruent in pairs, which would also mean like these two would be congruent too. They just were not needed for the problem. So we recognize the structure. We know we have vertical angles, and therefore they're congruent. That informs the equation. There you go. That's vertical angles. Okay. Questions for me? What questions do you have for me before we move on? Sweet, and we're moving on. Okay, so we're going to use that same kind of like note-taking structure for the other ones. So we have something now called linear pairs. Before I kind of reveal the definition, I bet we can predict what it has to do with. When you use the term linear, what does that mean? What does it refer to?
Line?
Absolutely. So linear refers to line. Pairs, of course, like groups of things together, two typically, but not only ever two. When we talk about linear pairs, we're talking about two or more angles that add together to form a straight angle or a straight line. That's where the linear part comes in. And these angles have to be adjacent. So get that down and we'll talk about those terms. Okay, so we're talking about linear pairs, two or more angles add together to form a straight angle or a straight line. Sometimes it's actually more intuitive to start with that straight line. And so when we talk about linear pairs, let's talk first about like a line. And then I need two or more angles that add together to make that line. So kind of designing that backwards, we're just gonna break this line up into multiple angles. And so if I add, say, like a ray or a line segment, I've effectively now create an angle on this side, which I'm going to call angle 1, and another angle on this side, which I'm going to call angle 2. The way that I use those arcs, what can I not say for sure is true about the two angles?
They're not congruent.
Yeah, so notice the way I said that awkward. That means they very well could be congruent, but they're not guaranteed to be congruent. Very sharp catch. But what we do know is they come together to form one continuous and straight line. And so if I start like on one end and go all the way over to the other end, combining the two angles together, I would indeed have that line. Having said that, what's got to be true if I add angle 1 and angle 2?
They equal 180 degrees.
Absolutely. So if I take angle 1, actually let me modify this a little bit. If I take the measurement of angle 1, so that little m means measurement, and I add it to the measurement of angle 2, that should equal precisely 180 degrees. Now, for this reason, when you talk linear pairs, you have to talk about them being adjacent. Adjacency just means they're pushed up against each other. In other words, they share a common wall or line. And so if you picture like a room in school, the adjacent room is literally next door. And it's adjacent because they share a wall. If they're across the hall, they are not considered adjacent. Adjacent. In this particular case, the shared line or the shared wall would be the ray that actually created the angles. And so because they share the blue ray, we do consider them adjacent. All right, so in terms of an example, no surprises. Okay, we have one continuous line. Okay, and then we have looks like a ray again that broke it up into two adjacent angles. Here we have essentially like angle 1. And here we have like angle 2. Okay, in terms of relationship, okay, we do have linear pairs. But just like last time, simply saying linear pairs isn't enough. Linear pairs actually drives another relationship, and that's going to be this term supplementary. Now, hopefully that's review, but supplementary is just a geometric way of saying they add to 180 degrees. So that's all supplementary means. Now, there is a slight like catch here that I want you to be careful of. Linear pairs are supplementary, but you can have supplementary without having linear pairs. Okay? And so supplementary is kind of a generic term, meaning it adds to 180 degrees. And so linear pairs kind of grab supplementary from like the generic area and applies it to itself. For example, do you guys know what the three angles of a triangle add to?
360.
Not 360.
180.
Yeah, you guys don't need to write this down, just watch. And so if I take these three angles and add them together, I'm going to have an under 180 degrees. So what can you say about these three angles? What can you call them?
They're supplementary.
But they're not linear pairs. And that's the difference I'm trying to kind of demonstrate here, is that linear pairs are always supplementary, but you have examples of things in the world that are supplementary without being linear pairs. Okay, so I just want you to be careful with that. Okay, because again, supplementary is just a generic term. Now, having said that, because we have something that's supplementary, we automatically know that we're going to add two or more things together to equal 180 degrees. We have an addition relationship or an additive relationship that hits a specific total. In this case, 180 degrees. So just like before, what are the pieces I'm going to add together to make 180 degrees? From our example.
78 degrees.
Okay, which is a measurement of angle 1. So that's going to be 78 degrees.
5y plus 2.
Which is going to be the measurement of angle 2. So we have 5y plus 2. And that's going to hit our total 180 degrees. Okay, and remember, it's 180 degrees because they do form a straight line, and straight lines must
Where
be
did the
right.
5y come from? We had. Never mind.
Okay.
The 5y looks like a 6 for me. Sorry.
Okay, so now in terms of solving this, I think we do have two ways to solve it. The most straightforward brute force approach would just be to solve the thing, right? And so we do a little simplifying. 5y plus 80 equals 180. Because we had the 78 plus a 2. We subtract 80 from both sides, we get 100. And then we get y to be 20. Now, of course, 20 is not the answer. 20 is just a y value. We'll do a substitution back into our original angle 2 to get our angle 2 value. So let's see, 5 times 20 plus 2 should be 102. Which, let's be honest, we could have predicted that from the very beginning. Can someone explain to me now how we could have known that was 102 before we solved for any kind of y value?
Subtract 78 from
180 minus
180.
78.
Yeah, and so since we know this entire line has to be 180, we knew that had to be 102 from the very beginning. And so certainly someone's now asking themselves the question, well, could I just set up an equation 5y plus 2 is equal to 102 and solve it? Yeah, 100% you could totally do that. I have no problem with that whatsoever. But in general, the big picture thing I want you to see is that, again, we have this structure, linear pairs, where you have a line cut into multiple angles. Linear pairs by rule have to be supplementary, which means they have to add to 180 degrees, which means we have something plus something equals our total. In this case, our total is 180. Okay, what questions do you have for us before moving on? Okay, can you guys just give me a rating again? Let's do a quick 1 to 4. 1, totally lost, have no idea what's going on. 4, feeling really great. You can put in the chat or just like flash a hand up to me, up to us. Ooh, chat. 3.1, I appreciate that, Myron. 3.5, okay, cool. And so just to let you know how I'm kind of reading it, if you're a 1 and a 4, easy. 1 is you're lost, you need a lot of help. 4 is like you're feeling totally fine, we can keep going. If you're saying you're a 2, what you're saying to me is like, hey, I kind of get what you're saying, but I'm not sure I can solve these problems on my own without a bunch of help. If you're saying you're a 3, the way I'm reading it is like, you feel like you probably could, but you're being cautious and maybe a little apprehensive because you don't know exactly what kind of problems are coming next. That's kind of what I'm reading. Okay, so just know that when you're rating yourself, that's what I'm thinking too. But it sounds like we have an opportunity to move on, so let's keep moving on. So this one addition relationship, it stands to reason to ask, are there more addition relationships? Well, there are. There's actually going to be a couple. Complementary is going to be our next one. All right, so again, no big surprise here, right? If you think about the major structures in geometry that we talked about really since like day 1 or 2, like we always talked about a straight angle or opposite rays, but we also brought up complementary right away or 90-degree angle right away. So in terms of complementary, just so like we have the right idea, okay, we are talking about like an intersection kind of relationship that we have this 90-degree angle. But just like linear pairs, what if they're cut up into multiple parts? What if there is now an angle 1 and an angle 2? But instead of stretching out over a whole line 180 degrees, we're trapped in this perpendicularity 90 degrees. Well, it's not a stretch to realize, and what we're saying is that if we take the measurement of angle 1, add that to the measurement of angle 2, that should equal a total as well, but in this case, it's 90 degrees. Okay. Now, again, the key, what you're looking for here is, of course, like this 90-degree intersection and some kind of bisecting divider, or no, I'm sorry, some kind of divider, not necessarily cutting in half. Well, but we clearly have like an angle 1 and an angle 2. Okay, so the relationship here is that you basically have perpendicularity. But that means we have really complementary relationship. And that means it's going to sum to 90 degrees. And that doesn't matter if it's cut into 2 angles or 15 angles. As long as the sum total goes back to a right angle, we can call them by this designation complementary. And that's the word you have to lock into your head. That's the one you're going to hear the most. In terms of the equation, going right back to that frame, I don't think it's going to be different than the last one. The only big difference, I guess, is that we're equaling 90 here instead of 180. But we still do have 2 parts. This may be a little hard to read on screen, so I'll read it off to you. The first angle is going to be 7x minus 17. That's going to be angle 1. 2 is going to be 5x minus 1. Okay, and that's going to equal the total, which is going to be 90.
Can you slow it down a little?
I can wait a second. It's that driver in me took over. So as you're kind of catching up, just as a quick like overview to repeat, this is really not different than linear pairs, except that the total is different. And that total is different because we're not dealing with a straight angle anymore, but instead we're dealing with a right angle or perpendicular intersection. But this says the same thing. I can cut that intersection up into multiple angles, and then the sum of those angles has to be equal to the entire angle, in this case 90 degrees. That's ultimately where I'm getting this addition relationship. Measurement of angle 1, that's what that little m means, plus a measurement of angle 2 is equal to 90 degrees. Now from here, and again, like if you know the next step, please don't wait for me. We're just going to solve down to x. So we have 7x and 5x makes 12x's. So we'll add 18. Cool. So in terms of getting x, well, this is no secret. We're going to substitute back in for x. So can you guys take about 15 seconds, and then I'm going to ask what angle 1 and angle 2 are worth in terms of degrees. Okay, so what is the measurement of angle 1, please?
46.
46 degrees. So this is 46 degrees right here. Okay, the measurement of angle 2, please.
$44.
Okay, and I would claim that you can get that 2 different ways. Way 1 is, of course, just plug in 9 back into the original. So 9 times 5 minus 1. What's the other way we could have gotten 44?
Subtracted 46 from 90.
Yeah, because we know the total has to be 90, so we can take advantage of that. 90 minus 46 makes 44. Either way is equally good. Okay. Now, of course, there is a danger in the second way. If you mess up the first calculation, the second one has to be wrong. If you do it by subtracting, if you do it by plugging back in, if you made that mistake, you certainly notice it. So we have an addition. So we have a congruent relationship, vertical angles, where they occur crossing each other like scissors. We have an addition relationship that adds to 180, making a straight line. We have an addition relationship that adds to 90 because it goes to a perpendicular or has perpendicularity. They mean the same thing. So now I'm going to pose a question. What if we have an additive relationship? So you have an angle, and it's cut up into multiple parts, but the total is not 180, nor is the total 190. I'm sorry, 90. So in other words, it's not complementary, nor is it supplementary. What we're left with is actually a model off the segment addition postulate that you went over with Ms. Jaco last week. But it does stand to reason logically, if I can take a segment and cut it up into multiple parts, then certainly I can take an angle and cut it up into multiple parts. Okay, and that's all the angle addition postulate. And keep in mind, postulate just means rule. That's all it really says. Okay, so for example, let's say I have this angle, and it's neither a 90-degree angle nor is it a 120-degree angle. Just for the sake of argument, let's say this angle, which I shall call ABC. Let's say the measure of angle ABC is equal to 120 degrees. Well, if I take this angle, and again, cut it up into multiple parts, where I know this is angle 1, and this part is angle 2. Okay. That just means I can add them together to make 120 degrees. And so it may be the case that this is like 20 degrees, which would force the second part to be like 100 degrees. Okay. And again, not a huge stretch, but if we can have totals that add to 90 and 180, certainly we could have angles that add to 120 and mimic that relationship. For example, now the additional thing to note is that you do have to know another piece of information. With linear pairs and complementary, you're not directly told, but you do know the angle total. It just happened to be 180 or 90. If you generalize the case, you're going to have to somehow know what the total angle is, in addition to like angle 1 or angle 2. But the relationship works similarly. So this doesn't have like a fancy name or anything, but like that's going to be the relationship. So we should immediately inform a new equation. Okay, so we'll go in that first spot.
Hey, Mr. Collins, could you slow down a little bit?
I can, sure.
Thanks.
No worries.
Okay.
So what should go in that first blank?
X plus 7.
Yeah, so it's going to be literally the measure of angle 1, or in this case, x plus 7. And the second blank?
2x plus 19.
Which is the measure of angle 2. And the third blank?
74.
Which is the total, or the whole angle. Okay? And so again, hopefully you're kind of connecting that this is not dramatically different than the last two examples. The only thing that's really different is that the total is not as set or predictable as a 90 or a straight angle 180 situation. Okay. The solve here is the same though. So we have x and 2x. Okay, so we subtract off the 26 from both sides. We have 48. And then x in this case would be 16. Okay. For the sake of time, I'm not going to go back and substitute those angles, but certainly you can when you're kind of reviewing your notes. And that we should be able to confirm that's a total of 74 by adding those back together. So just like the the segment addition postulate for segments, we do have an angle addition postulate for the angle sets. Now, if you're noticing that there's a whole lot more angle information or angle relationships than like segment relationships, you're absolutely right. In fact, in geometry, it's usually quite easy to prove angles are congruent or have a certain relationship. It's actually very tough to prove segments have that kind of relationship, which is why so much of geometric work centers around angles. Okay, let's do one more and I think we'll be done here. So are there any other special cases? So hopefully you've noticed that the relationships are kind of falling into two categories. I add things together to get a total, or the two things are going to be congruent and therefore equal to one another. So we do have a general relationship, a bisector, that actually occurs in angles as well. I would say this is a special case of angle addition postulate when the two angles in question are going to be perfectly congruent. So when I say it literally means to cut in two pieces, I mean it. So the term bi refers to two. Sect means to cut. Okay, which also means we can trisect. That means cut into three pieces. Quadsect, cut into four pieces. Quintuple sec, which means cut into a whole bunch more pieces. Okay, so what does this look like? Well, if I have an angle, and it doesn't necessarily have to be a right angle, it doesn't necessarily have to be a complementary angle. I just have some angle, which I'm going to call ABC. Okay, what happens if now when I cut into multiple angles, I cut it in such a way that angle 1 is precisely congruent to angle 2. And please notice here I'm using the same arcs on purpose because I want to show angle 1 and angle 2 are indeed congruent. Just as point of order, the thing that did the cutting is called the bisector. Okay, the OR in the end as a suffix means it's the thing performing the action. Like that's why you go to see a doctor. The OR at the end of the name doctor implies that person is the one doing the healing. The relationship, because they're congruent, would imply that the measurement of angle 1 is the same as the measurement of angle 2. Okay. And part and parcel, angle 1 and angle 2 are congruent. Okay. So let's see that in action. In this diagram, they cross their arcs. That's not uncommon. So if you see something like that, it means the same as them being congruent because they're using the congruency symbol for the arcs. But this would be like a classic example. Notice that you don't know the total amount of the angle, at least not directly. But intuitively, how big is the entire angle that I'm currently outlining in pink?
52 degrees.
And how'd you get that?
26 plus 26.
Yeah, okay, so unlike the angle addition postulate where you have to have the total, you don't have to have the total here because it's kind of implied in the problem. Okay, so we notice that we have a bisected angle. So bisect means congruent halves. So structure informs the relationship. The relationship informs the equation. We should have two things equal to one another. In this particular case, what two things? Like what goes in the left blink and the right blink?
26 degrees.
Yeah, so 26 can go here. And the right blink?
5x plus 11.
Quick question. I think that was that Wyatt that just answered. So anyone who, but Wyatt, who I think just answered, or no, Brett. Is that Brett? Okay, anybody but Brett. Does it matter which side you put the angles on? Okay, so Delaney, you're shaking your head no. Can you tell us why?
I just think no. Is it because they're the same?
And if they're equal, then certainly it can be read either way. And so is it true that like 2 plus 2 is equal to 4 in the same way 4 is equal to 2 plus 2?
Yeah.
And so, yeah, so this one you can really do either one because it's bisected. Now, again, in terms of solving, breaking down to algebra, subtract 11 on both sides, we'd have, 15 is equal to 5x. Therefore, x is equal to 3. And quickly confirming back in our answer, 5 times 3 is 15. 15 plus 11 is 26, so that's going to check out. Okay. All right. Questions for us? What questions do you have for us before moving on? Cool. All right. So where'd it go? Okay, that's about as close as I can get. So I have 6 quick examples. On these examples, I want you to kind of identify the geometric relationship, set up and solve the equation, and then go back and find the angles. That's going to be the natural rhythm of really all these problems. So what I like to do is to take you guys and put you into breakout rooms. So I'm going to come back and share this screen. What can I do? Well, I can. Okay, cool. Okay, so I'm going to put you guys into kind of randomized breakout rooms. When you get into those breakout rooms, can you please work on these problems? I'm not entirely sure if the screen is going to stay shared when I break you guys out. So can you guys like maybe take a quick screenshot of this just so you have access to it? I don't know how you guys know how to take screenshots, but here's what I would do if I were you. I'd go to your search tool and typing snipping. Snipping as in like scissors, as in like vertical angles. But go to your snipping tool. When it pops up, where'd it go? Just go to new. Okay, so go to new, and then you can drag around the problems, and then you screenshotted it, which I know is super complicated compared to like every other system in the world, but these are our computers, guys. Okay, so once again, if you didn't quite see that, search for snipping, select the tool, go to new, so new right here, and then drag around the problems, and then you have them. Okay, so breakout rooms. Hey guys, any questions I can answer for you on these practice problems?
Can you share the screen? Okay.
Can I share the screen back? All right, everybody, let's just run through these really fast to make sure you have a sense of what you should be looking at. This is going to get a little messy just because like the space involved, but we should be able to include all the necessary pieces. So again, the rhythm here is recognize the structure, so see something, identify it clearly with the relationship, and the relationship should inform how we're going to solve for the value. So taking this first example in the upper left, what's a geometric relationship we should attach to it? Like, what are you guys seeing?
Vertical angles.
Yeah, absolutely. Vertical angle is what we're looking for because we have an intersection of two angles, just like scissors, except like the blades and the handles are like up and down. But these are 100% vertical angles. Now, sometimes this is referred to as a vertical angle theorem. We're not going to stress about the word theorem right now, but its base word is in theory, which means it's kind of like what we think is happening. We'll talk more about that in detail in the next chapter, but it's definitely vertical angles. So what kind of relationship should we be looking for? Like, what do we know about vertical angles?
They're congruent.
They are indeed. Thank you. So we're looking for a congruency relationship. So something equals something because they're congruent, the same as. In this case, of course, it'll be 9y plus 7 and 2y plus 98. Okay, now, if you can get this far, since the only thing left is algebra, you should have confidence that you can finish out the problem. Okay, take away 2y from both sides, we have 7y. Take away 7 from both sides, we have what, 91? Yeah, 91. Okay, and so now we'll just solve for y by dividing. Okay, we have y equals, I have 13. Okay. Now, if you get this far and you solve the algebra, again, please pay really close attention to the question itself. This is asking you to find the angle value. And so when plugging back in, we have 124 degrees for the top one. So automatically, what should we get for the bottom one?
124.
Yeah, and we can certainly confirm that by plugging back in, we have 124 degrees. Moving on to number 2, what's the relationship that we see?
$180.
That's not the relationship. You're jumping ahead to the equation.
It's an acute angle.
We do have acute angles, yeah, but now we're looking for the relationship amongst two angles.
They're
Linear pair.
They are linear pair because they together, the 2x and the 48 will form a straight line, the EGH line. Therefore, these are going to be linear pairs. And linear pairs we associate with being supplementary. Okay. And so that informs the equation. I think it was already said. We have a sum total to 180 degrees, and we do have to say that properly. We can't just say they're going to be 180 degrees. That implies they're both separately 180 degrees. We want to say they add to 180 degrees. In this case, we have the 2x, and we have the 48. Okay. Now, in the interest of time, I think I'm just going to continue on from here because the last step is algebra. I feel confident that you guys can continue and solve that equation. The big piece of geometry for us is going to be identification and setting up that equation. And so let's just go ahead and move on. On number 3, what relationship are we looking at? I'm sorry, a little bit louder.
Complementary.
Complementary, yeah. And the big giveaway is that we have this nice 90-degree angle right here. We do have 3 angles. Angle 1, angle 2, and then we have a third angle right here. It doesn't matter how many there are. This is still going to be complementary. And that's going to be because of that right angle or the perpendicular intersection. Complementary, by definition, adds to 90 degrees. Okay? And just because now we have a third one, that's not going to change it. So we have the x plus 3, we have the x minus 1, and then we have the x plus 1. Okay. And again, we're gonna pause. We're gonna go ahead and stop there in terms of like solving it. You would have to solve down for x and then go back and find the angles. But when you do that, you should find that those add back to 90 degrees. Again, just in interest of time, I'm gonna pause that. Okay, moving on to example 4. What does this picture imply that we should be using?
Angle addition of postulate.
Yeah, and the giveaway here is that we don't have a straight line, we don't have 90 degrees, but we do have multiple angles, and we're given a big total here. And so this is going to be the angle addition postulate. Okay. That implies an addition relationship with a total that's it's fixed but not going to be common. Okay, and so we have angle 1 to be 6x minus 11, 2 to be 4x minus 25, and the total in this particular case is 124. Okay. So we have a congruent relationship with vertical. We have addition relationships with linear pair, supplementary, and angle addition. Okay. And again, your individual practice would be solving that down and confirming the answer. How about this one? We have no total here. So what relationship would we have? This would be the hint.
Bisector.
Thank you. Because this guy right here is a bisector. Okay, bisectors have congruent relationships, which means we have two things that are the same. X plus 40 and 3x minus 20 would be the same. Okay, I'm going to save example 5. That might end up being your opener tomorrow or something. We'll see. But certainly you could attack it independently as you wish. Okay, and so what's your job now? Like, what's your job individually? Well, first of all, you definitely want to finish solving for X on your page just to make sure you can do it. You can go back and check your answers individually. You don't really need a teacher to confirm that for you because you know how they should be behaving. So make sure that you go back and do that. Number 2, summarizing your notes. Like, ooh. That's always going to be a big thing, especially now that you've done some example problems. Hopefully you have a better grasp on what's going on. If you don't, you should probably do a little bit of practice first. Okay. If you go to our Schoology page, I'm just going to preview it for you guys. Okay. So here's a note sheet. I'm going to drop the video that I'm currently recording in here as well as soon as it finishes rendering. This right here is class practice. It comes with a key. This is also class practice. We're calling it cycling homework because it has problems going all the way back to like the first section. And so this is going to be valuable like review practice as well. This has a key. Remember what that means is none of this is to be turned in. This is independent practice. Okay, this is designed to help you prepare for Thursday's assessment. The other assignment that you have, if you click on today's agenda, you do have an assignment in our online book program called Savvas. Last Wednesday, you were asked to access a few videos and set up some accounts. The Math Excel assignment is actually in your Savvas folder. It's already assigned and preloaded. That's not really due until test day. And so you can work on that kind of over the course of the next 3 days. Okay? And so if you're not quite sure how to access Savvas, there's a video here to help you do that. If you're not quite sure how to handle Math Excel, here's a link to have you do that. Okay? This is a district assignment. It's not one that I have chosen to give you, but it's one that Columbia Public Schools has chosen to give you. And so there's going to be some weird questions in here. I'm not going to lie to you. There's some weird questions in here. And so there's lots of like help videos and links that can help you understand how they expect you to answer it. But please know that this right here is going to be frustrating. So like the stuff you're seeing here is directly related to how we have presented it and seen it in class. This is how the book has chosen to present it to you. Okay. And again, if you didn't do that last Wednesday, but in the next 4 days, make sure you access Savvas and such. The short version is you can go through the portal. And so if you log in through the portal, there's a button that actually takes you to Savvas, and your logins are going to be the same as your school logins. Like that's the super short version of it. These videos will tell you more. Okay. Having said all that, what questions do you guys have for us about what to do to practice and get better at this stuff? Okay, so can you give me one last thing just so I kind of know where you guys are on this, at least in my own head? Can you give me one more rating for the entire day? So like 4, you're feeling great about all this stuff. You know that you have to practice, but you're confident the practice is going to go very well. 1 would be like, oh crap, I'm not going to be able to do this on my own at all. Okay. Now, again, the way I'm reading a 3 is that you're pretty confident. I'm seeing a lot of 3s right now. You're pretty confident, but you know you're going to have to do some practice to get to bump yourself up to a 4. Okay. 2 means like you're probably going to have to maybe schedule some time to Zoom with us or come into office hours or Zoom into office hours or something. Okay. I'm seeing a lot of 2s. I appreciate the 2.9 to 3.5. I think that's a confidence thing, Hannah. You have to be confident instead of giving a range. Okay. And you're certainly welcome to ask questions of us too. Okay, guys, that's all we have for you guys. About a minute to your next class. Okay, so appreciate you guys' time.
Bye, Mr. Collins.
Bye.
Hi, Mr. Collins.
Ms. Jacob, I'm gonna
Do you only want
restart the